Section: Introduction. In this section, we discuss a range of advanced techniques used in large language models, LLMs, like GPT-4, PaLM, and Llama that have shown impressive performance in various reasoning tasks. To improve the reasoning abilities of these models, we explore different prompting methods that can enhance their functionality and performance. We categorize these prompting methods into two groups: single-query reasoning and multi-query reasoning. Single-query reasoning methods focus on prompt engineering and aim to complete the reasoning process within a single query. For example, Claude appends the input query with "let's think step by step" to improve reasoning accuracy, while few-shot prompting provides task-relevant examples to assist in generating answers. On the other hand, multi-query reasoning methods use multiple LLM queries to explore different reasoning paths for complex problems, such as least to most, TOT, and GOT. However, both types of methods have limitations. Single-query reasoning often requires prior assumptions or specific examples of the reasoning process, making it challenging to design them manually for each task. Multi-query reasoning can be computationally intensive due to the recursive expansion of reasoning paths for each task. Additionally, both methods may overlook deriving general guidelines or insights from past tasks to enhance efficiency and accuracy in solving similar problems. To address these limitations, we introduce Buffer of Thoughts, BOT, a new reasoning framework that aims to enhance the accuracy, efficiency, and robustness of LLMs across various tasks. BOT includes a meta buffer, which stores universal high-level thoughts distilled from different problem-solving processes and can be shared across tasks. For each task, we retrieve a relevant thought template from the meta buffer and customize it with specific reasoning structures for efficient thought-augmented reasoning. To ensure scalability and stability, we propose a buffer manager to dynamically update the meta buffer as more tasks are solved. Our method offers three key advantages. 1. Accuracy improvement. By using shared thought templates, we can adapt high-level thoughts to different tasks, enhancing reasoning accuracy without starting from scratch. 2. Reasoning efficiency. Our thought-augmented reasoning leverages historical reasoning structures to improve efficiency without complex multi-query processes. 3. Model robustness. BOT mimics the human thought process, enabling consistent problem-solving and enhancing model robustness. Empirical studies show that BOT significantly enhances precision, efficiency, and robustness across various tasks. Our contributions include introducing BOT for improved reasoning, utilizing MetaBuffer for storing high-level thoughts, and implementing Buffer Manager for continual improvement. Our experiments demonstrate substantial performance improvements over previous methods on challenging tasks like Game of 24, geometric shapes, and Checkmate in 1, while being more cost-effective than multi-query prompting methods. Additionally, we discuss the concept of retrieval-augmented language models, which use external databases to enhance output quality, and prompt-based reasoning techniques that have improved reasoning capabilities of LLMs. These methods have shown promise in various tasks and benchmarks, but may have limitations such as resource demands and manual crafting of prompts. Our approach with BOT aims to address these challenges and enhance the reasoning abilities of LLMs universally across tasks. Section Summary. In this section, we introduce various effective prompting methods to enhance the performance of large language models, LLMs, like GPT-4, PaLM, and Llama in reasoning tasks. These methods are categorized into single-query reasoning, focusing on prompt engineering for improved accuracy, and multi-query reasoning, which decomposes complex problems into simpler subproblems. To address limitations in these methods, we propose Buffer of Thoughts, BOT, a thought-augmented reasoning framework that improves accuracy, efficiency, and robustness by utilizing shared high-level thoughts across tasks. Section: Analogical reasoning. In this section, we will explain analogical reasoning and our Buffer of Thoughts approach. Analogical reasoning is a helpful method for natural language understanding. Recent studies show that large language models, LLMs, can use analogical reasoning similar to humans. For instance, Analogical prompting and thought propagation encourage LLMs to create similar problems and use the solutions to solve a given problem. However, the solutions from these self-generated problems may introduce errors. The thought retriever method uses past thoughts to handle similar queries, but it focuses only on text tasks, not general reasoning. Therefore, there is a need for a more advanced analogical approach for complex reasoning in LLMs. Our buffer of thoughts, BOT, is a key part of our approach. We use a problem distiller to extract important task details and constraints. Then, we search in a meta buffer containing high-level thoughts to find the most relevant one for the task. After that, we customize the chosen thought with task-specific structures for reasoning. Finally, a buffer manager summarizes the problem-solving process and enhances the meta buffer with high-level thoughts. Complex tasks often have implicit constraints and intricate relationships, making reasoning challenging for LLMs. To address this, we separate the task information extraction and comprehension from the reasoning stage using a problem distiller. This distiller formalizes the task information, denoted as X, to ease the reasoning process. We condense and translate the extracted task elements to focus on essential parameters, objectives, and constraints. This helps simplify complex problems into high-level concepts for easier retrieval during reasoning. Inspired by how humans summarize guidelines for problem solving, we introduce MetaBuffer, a library of high-level thoughts for different problems. These thought templates can adapt to various tasks, improving LLM precision and flexibility. Our thought templates, stored in the MetaBuffer, are obtained from problem-solving processes and classified into categories like text comprehension, mathematical reasoning, and code programming. Retrieving a suitable thought template for a task involves calculating the similarity between the task description and the templates in the MetaBuffer. This helps in finding the most relevant solution for the given problem. Section Summary. In this section, we introduce the concept of analogical reasoning, which is a valuable technique for natural language reasoning and has been shown to be achievable by large language models, LLMs, like humans. We present our buffer of thoughts, BOT, framework, which involves a problem distiller to extract crucial task-specific information and a thought template retrieval process to enhance LLMs with high-level thoughts for complex reasoning tasks. The BOT aims to condense and translate complex problems into simpler structures, enabling LLMs to retrieve relevant high-level thoughts from a metabuffer for improved precision and flexibility in problem solving. Section: Instantiated Reasoning. In this section, we discuss instantiated reasoning for specific tasks. When we have a known task, we retrieve a template T_J and use it to guide our reasoning process. For example, in a chess problem, we update the board state step by step using the template. We then apply this instantiated reasoning to solve task X with the distilled information X_D and template T_J, resulting in solution S_X using the instantiated reasoner with a LLM. If the task is new, we prepare 3 general thought templates based on the task information X_D. Our bot assigns the most suitable template automatically. These predefined thought templates help guide the reasoning process effectively. We introduce a buffer manager to summarize key guidelines and insights gained from problem solving. This manager stores distilled knowledge in the form of thought templates, allowing for permanent improvements in reasoning accuracy and efficiency. To extract a general thought template, we follow a 3-step approach, summarizing core tasks, describing solution steps, and creating a general template applicable to similar problems. We also use in-context examples to enhance template generalization. After distilling templates, we update the metabuffer with new insights if needed. We calculate similarity between new and existing templates to avoid redundancy in the metabuffer. We evaluate our buffer of thoughts on various tasks requiring mathematical reasoning, algorithmic thinking, and creativity. These tasks include arithmetic puzzles, reasoning tasks, programming challenges, multilingual math problems, and creative writing tasks. Section Summary. In this section, we discuss instantiated reasoning for specific tasks, where we either retrieve a thought template for the task or use general thought templates if the task is new. We introduce a buffer manager to store distilled knowledge in thought templates, enhancing accuracy and efficiency in reasoning processes. Additionally, we propose a template distillation approach to extract general thought templates by summarizing core task challenges and designing solution steps, ensuring robustness and generalization in problem solving. Section: Implementation and Baselines. In this section, we implemented and established baselines for our buffer of thoughts, BOT, using GPT-4 as the base model. We conducted experiments and an ablation study using Llama 3-8B and Llama 3-70B on an NVIDIA A100 PCIe 40GB GPU. We compared our bot with various prompting methods. 1. Standard prompting. This basic baseline involves asking a language model, LLM, to generate a response directly from the input query without any additional guiding examples or instructions. 2. Single query method. This method includes zero-shot COT, PAL, and expert prompting, which use the LLM to analyze problems and generate reasoning steps. 3. Multi-query method. This method includes TOT, GOT, and meta prompting, which enable LLMs to make decisions by considering multiple paths and self-evaluating choices. Our bot consistently outperforms previous prompting methods in accuracy across challenging benchmarks, especially in tasks like Game of 24 and Checkmate in 1. Compared to GPT-4, our method shows a significant 79.4% accuracy improvement in Game of 24. We also outperform TOT by 8.4% in the same task and show substantial accuracy improvements compared to meta prompting in various tasks. Our bot achieves comparable reasoning time to single query methods while being more efficient than traditional multi-query methods like TOT. By leveraging historical insights and informative guidelines from thought templates, our bot adapts a more optimal reasoning structure for complex problems, reducing the time needed for complex reasoning significantly. We introduce a new evaluation metric, success rate, to assess reasoning robustness. Our bot consistently maintains a higher success rate across tasks, showcasing its generalization ability and stability. The distribution analysis of thought templates shows that our bot can effectively discover appropriate templates for different benchmarks, generating a greater number of templates for tasks with diverse scenarios. Section Summary. In this section, we implement and compare our buffer of thoughts, BOT, with various prompting methods, including standard prompting, single query method, and multi-query method. Our bot consistently outperforms previous methods in reasoning accuracy, achieving significant improvements in challenging tasks like Game of 24 and Checkmate in 1. Additionally, our bot demonstrates comparable reasoning time to single query methods while being considerably more efficient than conventional multi-query methods like TOT, requiring only 12% of the cost on average. Section: Distribution Analysis of Time Cost. In this section, we analyze the distribution of time cost for different components of our bot reasoning framework across various tasks. We found that distilling task information and template retrieval take less time compared to instantiated reasoning, which is more time-consuming. Overall, our bot shows a balanced distribution of time cost, highlighting its efficiency. We also observed a better trade-off between model size and performance with our bot. In tasks like Game of 24, word list sorting, and Checkmate in 1, larger models like Llama 3-8B and Llama 70B may perform poorly. However, when combined with our bot, these models show significant accuracy improvements. Our bot enables smaller models to match or even outperform larger models, narrowing the gap in reasoning abilities and reducing the inference cost for complex problems. Furthermore, we examined the impact of the problem distiller in our bot framework. Disabling the problem distiller led to decreased accuracy in models like Llama 3-70B and GPT-4, especially in complex tasks such as Game of 24 and Checkmate in 1. Simpler tasks like word list sorting were less affected because LLMs can extract key information more easily. The problem distiller plays a crucial role in extracting key information and constraints in complex problems, explaining the differences in performance. Moreover, we investigated the effects of the metabuffer in our bot framework. Disabling the metabuffer resulted in decreased performance in models like Llama 3-70B and GPT-4, particularly in tasks requiring complex reasoning. This highlights the importance of the metabuffer in addressing complex problems effectively. In our ablation study, we divided the process into 4 rounds and observed the impact of the buffer manager. With each round, the model with the buffer manager expanded the metabuffer and utilized thought templates from previously solved problems to improve accuracy continuously. In contrast, the model without the buffer manager did not show improvement over rounds. Additionally, the reasoning time decreased with the buffer manager as it enhanced inference efficiency by retrieving suitable thought templates from the expanded metabuffer. Despite the significant improvements in accuracy, efficiency, and robustness of our method, there are limitations when dealing with problems requiring human-like creativity. Our bot may struggle with such tasks that do not rely on specific thought templates. Additionally, initializing the metabuffer with a weaker model may lead to suboptimal thought templates due to limited reasoning ability. Moving forward, we aim to integrate external resources with bot to create open domain agent models and optimize the distillation of thought templates for more complex tasks.